In a previous project video of mine, I showed you how I created a photovoltaic off-grid system, which to this date works without any problems. But what I noticed in the comment section back then was that many viewers stated that a flat mounting on the roof is not ideal, which I do agree with. Not only does the panel get soiled more easily, but this mounting also decreases the airflow under the panel and thus the cooling, and also the power output, since the sun is hitting the panel more often at a sharp angle. So why did I mount it this way then, and not at an angle? Well, the reason is that it is not easy to spot that way, and thus will most likely not get stolen. But anyway, since I recently got interested in how much energy I'm actually losing due to the position of my panel, I will conduct a small solar tracking experiment in this video, which will hopefully turn out in my favor and thus let me sleep at peace once again. Let's get started. This video is sponsored by JLC PCB. One fact about them: you can easily find the tracking number, invoice and production process of your PCBs in your accounts, and easily order more PCBs of your old design through the reorder button, without having to upload your Gerber files once again. For this experiment, I will be using two, hopefully identical solar panels, with an open circuit voltage of 6 volts and a maximum output power of 1 watt. One will be placed on a flat surface, while the other one will be mounted to a solar tracker, which, like the name implies, follows the position of the sun, in order to maximize the power output of the solar panel. Both panels will be connected to a power logger and load, which will later reveal how much more energy the solar tracker system harvested. And with the execution of this experiment explained, let's get started by building the solar tracker. To move the panel in a circular manner and also in an up-down movement, I went with this mini pan tilt mechanical system designed by F. Bueno-net. I printed the 3 required parts with my 3D printer, which took around 4 hours. Afterwards, I mounted the base plate to a piece of wood with some leftover screws and got myself 2 SG90 servos, which will be used to move the whole system. I positioned the fitting accessory of it in the base plate and added the motor to it, which I then covered with the second 3D printed part. To it, I also added an accessory part of the servo, mounted the second servo to the third and last 3D printed part with screws, and then finally completed the mechanical system by combining the 2 pieces with an additional screw. And as you can see, the movement of the solar tracker was possible, but of course for the servos we need an electrical signal to move them accordingly. For that, I created this small schematic, whose components I connected to one another on a piece of perf board. And once I was getting close to finishing the circuits, I noticed that the most important components, the photoresistors, were not properly utilized yet. In case you are wondering, photoresistors are, like the name implies, resistors, which change the resistance according to how much light hits them. With lots of light we got a small resistance, and in darkness we got a high resistance. I wanted to mount 4 of them on a circle with wall divided segments, so that, for example, when the left side is dark, the motors rotate the system clockwise, and if the lower side is dark, the motors move the solar panel upwards. This way, the system will always follow the brightest light source. So I constructed the described circular object in 123D design, and once again used my 3D printer to create it. Afterwards, I enlarged the holes for the photoresistor leads, pushed them in place and secured them all with a bit of hot glue. Now, to mount the solar panel and the photoresistor setup to the mechanical system, I created an 11 by 9.5 cm piece of foam plastic, to which I firstly secured the solar panel with hot glue, after I soldered 2 wires to its terminals. Then I created a 24 cm hole in the top section of the foam plastic and secured the photoresistor setup there with hot glue as well. To complete the solar tracker, I added wires to the photoresistors, which I then connected to the perfboard circuits and secured the foam plastic to the mechanical system with hot glue. Along with the 1 kΩ resistors, the photoresistors build up a voltage divider, which creates a high voltage when the photoresistor is dark and a low voltage when it is illuminated. So after connecting these servos to the circuits and powering it with a 5V power source, it was time for programming. In a nutshell, I utilized the timer 1 of the Arduino's Atmega 3208P microcontroller in order to generate servo-compatible PWM signals, which I constantly alter depending on whether the lower, upper, left or right side of the photoresistor setup is illuminated. And after uploading the codes, I tested the setup with a flashlight, which seems to work without any problems, which means it was time to complete the experimental setup with my power logger. I built this one in a previous project video, so feel free to watch it if you want to understand how it works, or if you want to create one for yourself. Anyway, after connecting the logger to the remaining unmounted solar panel, I connected a potentiometer loads in order to determine the maximum power point of the system, which according to my calculations should be reached with a resistance of around 3150 ohms. But since we would never reach the maximum power at a higher brightness level with this resistor, I rather replaced it with 4 200 ohm resistors in parallel, which should be able to get us close to 1 watt. That means the flat solar panel setup was complete, but sadly, in order to conduct both measurements at the same time, I had to create a second power logger for the solar tracker, which took quite a bit of time. But once that was done, I hooked the solar tracking solar panel up to the power logger along with the 50 ohm loads and started the outdoor experiments. Now I let the two systems create electrical energy from solar energy for around 2.5 hours, while making sure that the systems logged all the data onto the SD card and the solar tracker truly followed the sun's movements. And after waiting for that long, the flat solar panel delivered a total energy of 10,345 mWh, while the solar tracking solar panel delivered 11,891 mWh. That is a difference of 15% more energy, which is not that bad. Of course, we have to keep in mind that this experiment was rather short, was executed around noon, did not utilize an MPPT method, and the solar tracker was limited in its movements. But since we know that a sun angle of only 45 degrees can decrease the power output by 30%, we can assume that through the day, especially during the morning and evening time, my solar panel might be missing out on around 20 to 30% of the possible solar energy, which is a fact that from now on I have to live with. Nevertheless, I hope you learned a little bit about photovoltaic systems through this video. If so, don't forget to like, share and subscribe. Stay creative, and I will see you next time.